Okay, so we have some pretty good ideas here about the reactivities of carboxylic acid derivatives. And basically the last thing we looked at was the Claisen reaction, where we talk about an enolate nucleophile adding to the carboxyl electrophile. We're going to talk a lot about enolates in this mini lecture too. It's going to look a little mysterious. We're going to lose some carbons, but it's all okay. Hang on. Okay, let's start where we left off with looking at Claisens in terms of making new molecules. So our bell and whistle synthetic target is that we're looking for a 1,3-dicarbonyl. So when we see that kind of functionality in our target, we know that we can make this by a Claisen reaction. And as I showed you at the last mini lecture, we could in fact think of this Claisen as this enolate plus this diester. This is called a carbonate, or it could be the enolate from this guy plus this ester. So in theory, both of them will give us the same target, but only one of these is going to work really well, and that is this one, because this guy is going to lead to the possibility of a crossed Claisen, right? Because if I look at this enolate, it could certainly deprotonate the alpha hydrogens of the second ester. Then I have two different kinds of enolates running around in my beaker, two different kinds of electrophiles, and like I said, yuck. Not so good. So the way to go here is definitely to work backwards and make this guy from the addition of, we'll just put a generic R group because it really doesn't matter what the ester is. It's just going to the alkoxy is just going to get kicked out. And that was an interesting move there. We'll add that to this enolate. That should give me that target. Okay, and of course we get that by deprotonation of this ketone. And right here we see we have a problem as well. We're going to have some selectivity. We're going to have to make the kinetic enolate on the methyl side and leave alone the alpha hydrogens that would be leading to the thermodynamic enolate. So that means using something like LDA and keeping it minus 78 nice and cold. We can probably pull that off. And then where should we go? Well, I'm not telling you anything. I'm not saying use this starting material or use that starting material, but we know we can perhaps make this from the alkyne, in which case that's our starting alkyne. Let's see, we could definitely make that from, I'm having a little trouble with that angle. Could definitely make that from this alcohol by oxidation. And where could we go from here? Well, if I go the alkyne route, I'm going to break that bond to make an acetylide plus this alkyl halide electrophile. If I go the alcohol route, of course, we know we can do all manner of disconnections to make this be made from, say, that organolithium plus this aldehyde, and so on and so forth. So we can go back and back and back and back, but basically the first step backwards, that's telling us it should be a Claisen. All right, with that segue, we're going to talk a little bit about leaving groups as we keep trying to pull it all together in preparation for the final. So what makes a good leaving group? Way back in the 2301, if I wanted to try and do this, I'd say, no, I can't do that because hydroxyl group is a terrible leaving group. Br minus cannot kick out OH minus because OH minus is not that happy with that negative charge. It's a strong base, which means it's a lousy leaving group. So a good leaving group is a weak base, which means it's stable with that extra pair of electrons. So for example, if I really do want to kick out that hydroxyl group in some way, break that carbon-oxygen bond, I'm going to have to convert that oxygen into something that allows it to be a good leaving group / weak base. And that basically means converting it to a sulfonate ester, for example. So, addition of tosyl chloride in pyridine, we know the reaction here is up, down, out. That takes us to our tosylate ester. Great leaving group. So now when I've got my nucleophile in the next step, boom, easy peasy to kick that out because of course that is a super weak base. This is really very closely analogous to, say, sulfonate, or sulfate I should say. Well, the conjugate acid of sulfate is, woohoo, sulfuric acid. Super strong acid, super weak base. Really easy to kick out. So, what about this guy? You recognize this, I hope, as the product of an aldol reaction. And perhaps you remember, I hope, that aldols are in fact reversible. So, that's actually a good leaving group. Not the greatest by any stretch, but if I kick that down, I can kick out the enolate to remake the starting materials from my aldol reaction. So there's my leaving group. A reasonably weak base because I delocalize that negative charge via resonance. Similarly, if I have this carboxylate, it's delocalized, and that's neither here nor there. What I'm trying to show you is that it too can decompose to kick out an enolate. And in this case, what do I kick out? Oh, holy cow. I kick out CO2 and the enolate. And CO2 bubbles out, making this a really quite facile reaction. So the take-home message here is, yes, enolates can be leaving groups. And we're going to see that in this next example. It's really important that we see how this works because it's really useful in synthesis. So, for example, if we look at this beta-keto ester, what you, I hope, remember from the acid-base chapter is that those guys, they're really pretty acidic, okay? Certainly as acidic as water, more so even. And so, it's really very easy to deprotonate at that active methylene. Okay, so really easy to do this. Sodium carbonate potassium carbonate, no problem deprotonating that active methylene. Well, once you do that, you've got a good carbon nucleophile, and you can do any old SN2 you want to alkylate and make a new carbon-carbon bond. Big deal. We've been doing this forever. Well, why this is a big deal is because then we can magically clip off that CO2R group to give you this ketone. It's as if I started with this ketone on the left, which of course has all kinds of alpha hydrogens that could be deprotonated, but I only want to deprotonate and make the kinetic enolate. Well, here's the neat thing. Because of the structure on the top, where we're going to actually be able to get rid of that, this allows us complete selectivity for deprotonation of that methyl hydrogen. I don't even have to try. I don't even have to worry about a kinetic enolate. I don't have to worry about temperature. I don't have to worry about my base. When I deprotonate up here, it exclusively goes for that hydrogen because of the active methylene. It's much more acidic than any of those guys. Then all I have to do, add my halide as we've seen, and you've got your selective product. Alright, so it looks great. It looks like magic. It's not magic. It's not magic at all. Once you have alkylated your active methylene, all you have to do is hydrolyze your ester. So protonation of your carbonyl, followed by attack by water, up, down, out. Lots of proton transfers in there, and if you can make anything out of that mess of arrows, you're a better man than me. But basically, you should make sure you see how that mechanism works. It's the old mechanism we know already. So I've got my acid, not my ester, and now there it is, or there it is. But I'm basically just going to rotate around that carbon-carbon bond because that's the exact same thing. And what this allows me to do is set up some hydrogen bonding, intramolecular hydrogen bonding in this beta-keto acid now. So redrawing that a lot bigger so my arrows aren't such a mess. Well then, a paracyclic reaction can take place just like a reverse Diels-Alder. So that gives me loss of my CO2 right here plus that enol, which of course tautomerizes straight away to the ketone. And then we can just deprotonate in our workup to give our stable final product. So it's called decarboxylation for obvious reasons, because you're losing your carboxyl group and you're throwing away a carbon. That's kind of a problem, but it's very handy for synthesis. Makes life a lot easier. So for example, if I want to try and make this ketone from 2-butanone, you're probably going to look at it and say, well, it's pretty clear that makes sense, that would be the 2-butanone. And that's certainly screaming enolate chemistry. I would want to take this enolate and add this electrophile. So I can put a bromide on there, whatever I want to, tosylate, whatever. But you know, this is telling me I've got to come up with the selective deprotonation again. I don't want to deprotonate here. I do want to deprotonate here. So how can I control this? Ooh, very easily. If I could just put, say, something here that would be an electron withdrawing group that I can ultimately lose, then that's going to make this more susceptible to deprotonation. Well, do you see where I'm going? You just put your ester group there, and that's how we're going to go. We're basically going to start with this, add carbonate or whatever weak base you want to. That's going to take you to this guy and that guy exclusively. Add my benzyl bromide, SN2, and then H plus, H2O, heat, minus CO2, there is my product, because I have lost this by hydrolyzing to the acid and then decarboxylation. Very cool. So the next question is, could you make that from methylpropanoate? Well, actually, yes, you can, because if you think about putting in that mysterious electron withdrawing group and using that as your starting material, which is what we just did. Ah, looky there. It's a Claisen. It's definitely a Claisen. So I could make that from this, which is methylpropanoate, and this guy. Whoa, that's an interesting line. Which is methyl acetate. So it's still not beautiful, but what you want to think about in this examples of using these active methylene compounds is that, you know what? They can all be made by Claisen condensations. So that's it for this section. It's a very, very limited application kind of chemistry, but it's very useful. And it pulls together an awful lot of chemistry that you've already learned. So that's all, and we will have one more mini lecture for chapter 21.